Good day everyone, welcome to the Capstone 1 presentation for the Man-to-Machine Cohort 17 program. This project applies the knowledge and skills we've gathered throughout the program to a real-world challenge. Our project focuses on an area within artificial intelligence, mainly on food image classification using deep learning. In today's world where visual data is abundant and AI is rapidly advancing, the ability to accurately identify and categorize objects from images has countless of applications. Let's see. Okay. Let's dive deeper into the problem description of our project. As the slide highlights, in today's digital age, food images are abundant and found everywhere. They are constantly shared across social media platforms and are becoming increasingly central to nutrition and wellness applications. By accurately identifying what's in the picture, we can greatly improve a variety of services and user experience. For instance, smarter restaurant recommendations, suggestion dishes, or eateries based on visual preferences or past orders. It's crucial for calorie tracking and meal logging, allowing users to simply snap a photo of their food for instant nutritional information. Moving beyond tedious manual entry, it enhances the user experience in food delivery apps, improving search functionalities and even enabling visual menu navigation. Given this, our primary objective for this Capstone 1 project was to develop and evaluate a deep learning model capable of accurately classifying various food items from images. To tackle this problem, we used the Food 101 dataset. As indicated on the slide, Food 101 is a large and widely recognized image database specifically made for food image classification research. It was developed by ETH Zurich University, Zurich, Switzerland. This dataset is quite extensive, comprising a total of 101,000 images distributed across 101 distinct food categories or labels. For each of these 101 labels, the dataset provides a consistent split. We have 750 images designated for training in our model and 250 images set aside for testing its performances. We can easily incorporate Food 101 using PyTorch library, as can be seen in my Python model project using PyTorch. As you can see here, I simply imported from Torch Vision database and simply load it with a simple data loader. Okay. Now let's discuss our approach and model architecture. For our overall strategy, we adopted a highly effective technique in deep learning called transfer learning. Specifically, we leverage a pre-trained ResNet 101 model. ResNet 101 is a very deep neural network with 101 layers originally developed by Microsoft. The concept is simple yet powerful. We reuse the early layers of the ResNet 101 model. These layers have already learned fundamental visual features such as how to detect edges, corners, textures, and basic shapes. They are excellent general purpose feature extractors. We then replace and retrain only the final layer of the network, moving on to data pre-processing, which is a critical step to prepare our images for the neural network. We perform a few standard operations. First, we resize all images to 256 on 256 pixels. Then we apply the center crop to 224 by 224 pixels. This specific size is standard for ResNet model. ensuring the input dimensions matches what the pre-trained network expects. Finally, we normalize the pixel values using ImageNet statistics. This means we transform the pixel intensities based on the mean and standard deviation of the ImageNet dataset. This standardization helps the model converge faster and perform better, as the pre-trained weight were optimized for data with these specific statistics. Okay. Regarding our hardware of my PC, the training was performed on an NVIDIA GPU, specifically the RTX 3080, which provides 10 gigabytes of VRAM. Our CPU was an Intel i5 11400. For the learning process, we used the cost entropy loss function. As shown, the loss is calculated as the negative logarithm of the predicted probability of the true class. This loss function is a standard and highly effective choice for classification problems, especially when dealing with multiple classes like our 101 food labels. We trained our model for 3 epochs. An epoch represents one complete learning cycle over the entire training dataset. Finally, for our optimizer, we selected ADAM, which stands for Adaptive Moment Estimation. ADAM is a popular and advanced variation of the traditional stochastic gradient descent algorithm. It's particularly effective because it incorporates adaptive learning rates for each parameter, meaning it automatically adjusts how big a step to take during optimization, and it also considers a momentum from previous gradients. This combination typically leads to faster convergence and more stable training compared to simpler optimizing. Now let's move on to some of our visual results, which highlights the performance of our training model. We are pleased to report that our overall success rate for food image classification stands at 87%. This indicates that our model can correctly identify the food item in nearly 9 out of 10 images from the test set, which is a strong result for a dataset with 101 diverse classes. Let's take a look at a couple of examples here on the slide. On the left, we have an image of protein. Our model correctly predicted it as protein with a very high confidence, 97 to be exact. Let's look also on the middle. We have a simple image of pizza. Again, our model correctly classified it as pizza with 85 confidence. This specific picture was taken outside of the 101 database. That is why the confidence is a bit lower, but it shows how robust the algorithm is. While slightly lower than the protein, still a very strong indication for the correct classification. And finally, we identify ramen with 98 confidence. These visual examples, combined with our 87 overall success rate, showcase the effectiveness of our deep learning approach for food image classification. Let's discuss our lessons learned and improvement suggestions. First, a major takeaway is that transfer learning works exceptionally well. Our experience confirmed that leveraging robust pre-trained models like ResNet is a highly effective strategy, particularly when working with limited computational resources and time. Second, we recognize the profound importance of data pre-processing. Steps such as image resizing, normalization, and precise cropping had a significant impact on our model's performance. These pre-processing techniques are crucial as they prepare the data in a consistent format expected by the model and enable the model to work effectively with new unseen images and diverse datasets. We have several improvement suggestions. One key area is to fine-tune all layers of the network, which requires a stronger computational power than I have on my personal computer. It of course would lead to an even greater, better and higher accuracy. And additionally, we suggest exploring more advanced models. While ResNet is powerful, experimenting with architectures like EfficientNet or the more recent Vision transformers could yield potentially higher accuracy. And that's it. We conclude our presentation. Thank you very much for your time and attention. If you are interested in exploring the project further, perhaps reviewing the core data or detailed analysis, please feel free to check out on my personal GitHub repository. You can find all the resources at the link provided on the slide. Thank you.